Indian Institute of Technology, Guwahati. He has completed doctoral degree in 2018 at Indian Institute of Technology, Bombay. He has published more than 30 research articles in national and international journals and conferences. He is guiding more than 5 PhD research scholars. He has obtained 4 patents for the benefit of society. A list of patents are multi-station, multi-axis, hybrid layered manufacturing system, in situ stress relieving process for additive manufacturing, realization of the composite injection mold with conformal cooling channels through hybrid layer manufacturing, elimination of support mechanism in additive manufacturing through 5-axis deposition. We are honored with your presence, sir. Our current session topic is omnidirectionality in additive manufacturing systems. Now I request our resource person to proceed with the session, sir. Requesting, sir.
Thank you very much for the introduction. I just want to start with something like there is an internet issue here today. I'm again getting disconnected. I have tried it
Okay.
2-3 times. So I'll start. If
Okay,
I
sir.
fail, then I'm connecting it my mobile also. I have
Okay,
already downloaded the PDF file in my mobile. And
okay,
if I fail here, then I'll try.
okay, no problem, sir. No problem, sir. Sir, your voice is not audible, sir. Uh, uh,
Yeah. So like this, just it happened
oh,
once
okay,
again.
okay, sir. Okay, sir. Okay, sir.
So I'll try to connect from my mobile.
Uh, okay, sir. Okay, sir.
Are you able to hear me from this
Yes, sir.
device?
Yes, sir. Now is okay, sir. Okay, sir. Yes, sir.
Okay, let me try to share the screen from here.
Okay, sir.
Are you able to see my screen now?
Yes, sir. Yes, sir.
Okay. I think this is better. So I'm sorry for this, but I'll try to manage with this only today.
Okay, sir. Okay, sir.
Okay.
Sir, sorry to disturb you, sir.
Yes.
Sir, if possible, if you are sending to our team, our coordinator will share the screen, sir. You can speak from them, sir, if it is
That is
possible,
also
sir.
fine. But now I think I have opened it in the right device. Now I think it will be
Yes, sir.
visible.
Now it is correct, sir. Perfect,
Yeah.
sir. Perfect, sir. Yes, sir.
This is a convenient mobile. So I'm sorry, sir. I'll try.
Oh, okay, sir. Okay.
So good afternoon to everyone. My name is Sajan Kapil. Today I will discuss about a very interesting phenomena which is called as omnidirectionality in additive manufacturing. So far this phenomena was not really highlighted earlier by the experts, and we were using it since a long. There are unfortunately some videos I may not be able to show you, but In the end of the lecture, if the internet get established, then I can transfer to my PC and I'll show the videos also. So you need to see a bit carefully now to the diagrams, so that I will be able to explain you few things. So in this case, as you see on this right side diagram, there are two figures, one on the top and another on the bottom side. The top side diagram shows the latest type of DED system. DED means directed energy deposition system. While the bottom side shows the first, which was invented in 1989 by Professor William Steen, the conventional or the first DED system. So in this bottom side figure, you can see that laser is coming from the top, and the weld bead, or which is also called as clad, is spreaded on the substrate like on the bottom, and powder is fed. You can see that in this case, laser is coming from the top and powder is fed from the side. In that case, there are some issues, and that is why in the modern time they have switched to the top type of system, which I'm not able to show the video, but I hope you are familiar that the laser comes from the center and powder comes in a conical form from all around the laser. And such systems we are calling as omnidirectional additive manufacturing system. So this particular phenomena people are using in all additive manufacturing system, but we till now we were not able to identify or give a name to this. So recently we have identified this phenomena, and this work has been accepted in ASME very recently. So this is a very latest work I am going to present today. So I'll start with the introduction to additive manufacturing. Then I'll discuss about the omnidirectional additive manufacturing systems, a new definition which we are going to give, a property of additive manufacturing, machine tool basically. So far you might have seen a lot of things related to the process. Now today I'll discuss about the machine tool of the additive manufacturing system. It is very important phenomena when we really deal with the micro level manufacturing systems. I'll also discuss about the inherently omnidirectional systems. I mean, in which there is no need to put any extra auxiliary system to make them omnidirectional. There are some inherently omnidirectional AM systems also. Then, as per the ASTM, there are 7 processes of additive manufacturing: DED, material extrusion, wet photopolymerization, sheet lamination, powder bed fusion, material jetting, and binder jetting. I will discuss each and every process, and I'll try to explain how omnidirectionality can be implemented in these processes if they are not inherently omnidirectional. So one by one, I'll cover each and every process and show you, and you will realize that the system was already there, but we are the one who has identified it. So then after that, I'll conclude the presentation. So you already know what is additive manufacturing. So I'm not going to go into the details of it, but briefly I'll explain. Additive manufacturing refers to layer by layer fabrication of 3-dimensional physical models directly from computer-aided design. It is an automatic process of manufacturing objects, parts, prototypes, tools, and even assemblies directly from the CAD model without any cutter, tool, or specific or tool specific to the geometry. In this process, we start with the pre-processing of the CAD model. We do the tessellation, we do the make the STL file, then we do the slicing, we add these layers together and make the final part. In some cases, as you can see on this bottom side diagram, the droplet may fall down due to the large overhang, but as you see on the right side, if the overhang is less, they may support up to a certain level of overhang. If the bead is deposited or the material is deposited in the center of substrate, there is no issue. But if it is deposited on the edges, you may need some support mechanism. So we deposit the main material and support material, or the loose powder in some cases, or available material in some other form can be utilized as the support. Like this, we build the whole part, and in the end, we remove this support. That usually comes under the post processes. Also, as this process deals with layer by layer manner, the surface accuracy is not really that good. it depends on the layer height, which is in a very accurate additive manufacturing process, which is commercially available as well, is the powder bed manufacture. Powder bed fusion goes up to 10 to 20 micron, and hence you can imagine the RA value will be very, very bad. Hence, you may need a finishing operation. So that all comes into the post processes. So these are the 7 processes divided by ASTM, classified by ASTM. First is wet photopolymerization. We know that in wet photopolymerization, we have a tank full of liquid photopolymeric material. From top, UV laser used to scan the desired area, and hence the desired portion get cured and get added with the previous layer. In another process, which is called as material jetting, we inject the material on the substrate. It is nothing but like your 2D printer, but you can assume that in your 2D printer there is a z-axis and you keep on depositing the material, or you are actually injecting the material. The third process is called as binder jetting. In binder jetting process, we used to usually have a raw material on the bottom side in the form of powder bed, and from the top the binder material used to come. It used to deposit it wherever it is required, and hence that portion got after certain period of time got cured and become solid. The fourth process, which is the most extensively has been used till now, is material extrusion. In material extrusion, we extrude the material through a small orifice in the form of a molten material, and then it is collected on the substrate. Wherever it is get collected, it got solidified, and hence we build the final part. One example for material extrusion is FDM process, which you might have definitely seen. Sheet lamination is in the sheet lamination process, the raw material is in the form of sheets, and we kept these sheets together, and by some means we then join them. Different processes for joining it are like ultrasonic consolidation if you are dealing with metal, or you can put glue between the two sheets if you are dealing with some non-metals like paper or plastic material. The another category is powder bed fusion. This is another very, very popular process for metals. In this case, we spread a layer of powder on a bed, and then from top we used to write through a laser. Wherever this laser goes or scans, that area get melted and fused with the pre-built layer. In this case, usually if the overhang is less, the loose powder act as a support material. However, in the case of metal, usually we have to provide the support, and that is because of the residual stresses and warpage in the thin sheets. The last process is direct energy deposition. In direct energy deposition, we usually do not have anything on the substrate, and the powder or wire or sheet, or in the form of strip maybe, are fed into the molten pool, and that molten pool is created by some energy source like electron beam, laser, or a conventional welding process like TIG, plasma, or MIG. So these are 7 basic AM processes. There are different variants, but the core idea is same. All these processes built apart in a layer by layer manner. Now I've come to why ASTM has defined these processes in this manner. They started with wet photopolymerization and ended with directed energy deposition. This they have in line from wet photopolymerization to DED based on the energy consumption. It means wet photopolymerization consumes the least energy. So I'll give you an example also. Typically, in the SLA-based process or this wet photopolymerization process, the UV light which is used is of approximately 40 watt only, just 40 watt. Although, when you talk about directed energy deposition process, the laser used here are in kilowatts. Like the one we have in IIT Bombay as well is a wire-based DED system. The laser power is 4 kilowatt.
Sir, sorry to disturb you, sir.
Yes.
Sir, the presentation shared, we are not seeing the presentation, sir. Yes, actually, just now one participant shared a screen. That's why it disturbed, sir. I request, dear participants, please don't share your screen. and keep your mic in mute condition and don't switch on your video. Sir, sorry, sir. Can you share once again, sir?
Yes, sure.
Yes, sir. Yes, sir. Please, sir.
Okay. So it happened just because somebody else shared, right?
Yes, sir. Yes, sir. It seems, sir. It
Okay,
seems.
no,
Yes.
no. Okay.
Yes, sir.
Thank you for pointing this out.
Okay, sir. Okay, sir.
Now, is it visible?
Yes, sir. Visible, sir. But previously it is good, sir. Presentation mode. Yes, sir. Yes, sir. Yes, sir. Perfect, sir. Perfect, sir.
Okay, so
Yes,
okay,
sir.
so I am on slide number 6 right now.
Yes,
So
sir.
okay, so okay, I'll just explain it a little bit just again. So I was saying in ASTM they have classified from wet photopolymerization to directed energy deposition, and they inline these processes in this way because wet photopolymerization utilizes least amount of energy. Typically, the energy is in the range of 40 watt, while in the case of directed energy deposition, the energy consumed is in kilowatts. Like, for example, 2 to 6 kilowatt. So it is based on low energy consumption to high energy consumption. Now, as today we are going to talk about something called omnidirectionality, I will say, let me rearrange these processes based on the process which is not at all omnidirectional. We have to provide some auxiliary machine tool elements so in such a way that it becomes omnidirectional. Two, the processes, those are inherently really omnidirectional. There you need not to add any new thing. Based on that, as you can see on the bottom side diagram, DED is the one which is really not omnidirectional. And based on this is the most I'll say unstable process. The most stable one, or I'll say inherently omnidirectional, is the binder jetting. So based on this, the rank is DED is not omnidirectional, material extrusion also not omnidirectional, powder bed fusion also not, wet photopolymerization also not. Sheet, few cases there are few cases where uh, process is not omnidirectional, while material jetting and binder jetting are usually omnidirectional and doesn't give any issue. Now, as I have talked a lot about omnidirectionality, let me define. So the term omnidirectional indicates an equal sensitivity of the process in all the directions. In the context of additive manufacturing, omnidirectionality implies invariance of material and geometric properties regardless of the travel direction. Omnidirectionality, more often than not, is a property of setup or 3D printer. However, a few AM processes are inherently omnidirectional, while others are not. So we have to appropriately make them omnidirectional. So I'll just that is about the additive manufacturing. Let me just briefly tell you about the omnidirectionality in other systems. So on the bottom left side, you can see two diagrams. Omnidirectional antenna. Omnidirectional antenna used to receive signals from all the sides, while the directional antennas used to receive signal only one side. In a similar way, omnidirectional mic used to receive the sound from all the sides, while directional mic used to receive the sound only from one side. Omnidirectional wheel also you can see, and the directional wheel is the conventional which we use in our car. It can go only straight, while the omnidirectional wheel, can go in any direction without any turn in the axis. So I mean to say, if you talk about this omnidirectional wheel, it can go in any direction without any additional arrangement, and hence this is inherently an omnidirectional wheel. This video I could not represent, but you can note down it, and you can after the presentation you can see that. Just type on Google, you will find omnidirectional drones recently developed by ETS Zurich. In that case, the drone can even tilt and go in any direction. It's not like the conventional drones. So you will have some idea the importance of omnidirectionality. As I'm talking about in the terms of additive manufacturing, it is the property of the machine tool which gives the geometric and material property same in all the direction. But sometimes you may definitely say why you are calling it as omnidirectionality is nothing but isotropy. But at this point of time of discussion, it is important to draw your attention towards the isotropy and omnidirectionality. Isotropy underlies uniformity in the part properties, irrespective of the part orientation and location of measurement. While omnidirectionality, on the other hand, is associated with the machine tool. An omnidirectional AM platform promotes the fabrication of isotropic part. Anisotropy, which signifies with non-uniformity in the part property, can arise from several factors such as layer by layer nature of the additive manufacturing, thermal gradient due to the scanning, and solidification rate. So there are several reasons for getting the isotropy, anisotropy in the additively manufactured part. The very famous reason is we part in layer by layer. Usually, the strength of the part is less in the build direction, while in other two direction it that makes the part anisotropic, and this is because of the nature of the process itself. But on the other hand, omnidirectionality is in the machine tool side. So a omnidirectional deposition, which is often neglected, significantly contributes to anisotropy of the part itself. So also notice the definition of omnidirectionality as present here is confined to plane of deposition, unlike isotropy, which extend to 3 dimension. Like in isotropy, we can have in X, Y, and Z direction. For omnidirectionality, we'll talk about in the deposition plane, that is mostly XY plane. Now you can see in this diagram, I'll show the importance why we are so worried about the omnidirectionality. The left side diagram on the top side is showing a conventional TIG welding. In TIG welding process, we used to feed wire into the molten pool, and if you are moving on a rectangle geometry, then you can see when you are moving from A to D, if you just carefully look into this diagram, if I am moving from A to B, in that direction, in that time, it will be a front feeding. You can see on this small right side diagram also, a sub diagram of the left diagram. You can see that if I am moving from A to B, it will be front feeding. Then if I move from B to C, then it will become side feeding of the wire. And then if I move from C to D, it will become back feeding. Again, if I move from D to A, it will again become side feeding. So this is what is happening actually. You are continuously, either you are moving in a single layer only, but due to the non-linearity of the trajectory on which you are moving, you are having different feeding mechanisms. And there are a lot of issues if you are having different feeding mechanisms while moving on a single trajectory. How it can be eliminated? Just on the right side diagram, it is shown. If, for example, you are at point A and you are going at point B, no need to worry about. Only the bottom side, if it rotates, then you will find always front feeding can be maintained. So the importance here is at each location, at each location, the feeding mechanism is different. What is the issue? You can see on the bottom part. Serrations may happen in the deposition. So what may happen? The parameters, the feeding angle, the location of entering the wire into the molten pool, which are optimal for front feeding, may not be optimal for back feeding. And sometimes it has been occurred that the wire itself just serrated or just make a cut into the deposited path, and we get a cut like you can see here. This is called as serration in the deposition. The solid wire, which is not melted, just make a groove into the deposited bead. The second issue we have found is the deviation in the deposition bead. So if you see carefully, the melting location, if it is not on the center, then it will definitely change if you are moving in a non-linear trajectory, and hence you want to deposit the bead symmetric about the blue path, but what you will get is shown in this diagram. So there will be a shift in the deposition, and that is very, very, very important when we talk about the micro deposition. Although everything is fine, but due to the non-omnidirectionality of the process, you are depositing wherever at a location which is not desirable. The another one is variation in the substrate dilution. You see that on the left side, on the bottom right side diagram, if I'm feeding from the left side, Due to the projection of wire, the penetration will be less under that, and hence a asymmetric kind of beam will look like. But I can manage with it, and I can accommodate it in somehow, but this will keep on changing when the feeding mechanism will change, and hence your geometric property as well as your material property like strength will change from location to location just because of this phenomena. And that is why we are really worried about, and we want the consistency. If I talk about the TIG welding, I want the consistency in feeding mechanism. It should be either just the front feeding all the time or by some mean. So let us try to define this phenomena mathematically so that it will be easy for us to understand and follow further. I will define this definition will remain true for all the additive manufacturing processes. I'm saying that there are three vectors, and the directional sensitivity in additive manufacturing arises from the inconsistency between the spatial orientation of three vectors relative to each other, namely the source of fusion. As you can see on the left diagram, Vs is showing the direction of source of fusion. So the laser is coming from the top to bottom. That means top to bottom vector is showing from source to the point where the laser is striking is the vector showing source, vector corresponding to the source of fusion. That is Vs. Then there is Vf. Vf shows the direction of feedstock delivery. Now laser is coming from the top, that is always vertical, assume. Then how you are feeding wire or how you are feeding powder or any raw material into the molten pool. That is called as direction of delivery. And the third vector is travel direction. That is usually along the path on which you are moving. So these are the three vectors. I can say strongly, if these three vectors remain consistent relative to each other throughout the process will be omnidirectional. Otherwise, it is not going to be omnidirectional. It may behave unpredictably. There are some cases like in powder bed fusion, there is no delivery of powder. Powder is always on zero position, as you can see on this right side diagram. Pre-placed feedstock. This diagram you can see. In this case, Vf is zero. I mean, we are any powder into the molten metal. In this case, the powder is already zero. Hence, our Vf will be zero. Now only two vectors are there, Vs and Vd. That means now we will look into we will stick to our definition. If in this process the angle between the Vs and Vd is changing, that means process is not going to be omnidirectional. Vs and Vd, that angle between these two vectors should remain consistent. If it will change, then not at all the process can be omnidirectional. It will behave something else at one position and it will behave differently at another location. So how I can say the process can be inherently omnidirectional? In the right side, you can see the condition. If the vector corresponding to the source of fusion and the vector corresponding to the feeding material are parallel, and the deposition direction is perpendicular to the fusion vector direction or the source of fusion direction, in that case, process will remain omnidirectional. Otherwise, it may not. Examples I'm showing on this bottom side diagram. For example, you are dealing with DED. If you recall the diagram which I have shown in the beginning itself, let me go back to this point of time because it's very important. This diagram, if you see, developed by William Steen, where powder is fed from the side, laser is coming from the top, and you are moving in some direction. In this case, just you look at this. What is happening? If I'm moving at a non-linear trajectory and I'm taking a turn, then definitely the angle between Vf and Vd may change. Also, the angle between V and Vs may also change. Hence, definitely this process is not going to be omnidirectional because of this variance in the change in the angle, the delivery direction, feeding direction, and the vector direction. This may happen because I'm moving up and down, or due to the inclination of the fusion source and travel direction. In that case also, it may happen that the angle between these two may change, or hence we will get the non-omnidirectionality in the source. Now, let us discuss one by one each and every additive manufacturing process defined by ASTM, and we will also discuss about how people are achieving this omnidirectionality, although till now they have not given any name to this phenomena, but they are doing it somehow. So for the directed energy deposition based AM processes, the feedstock is fed instantaneously along the vector VF into the molten pool created by the fusion source. Hence, the relative position of along the source of fusion, that may be laser, VF, direction of delivery of the powder, that is the VF, and VD, which is the direction of deposition. They may vary when following a nonlinear trajectory in XY plane. It is obvious. Although there are different type of DED processes. For example, we talk about MIG welding based. In MIG welding, the wire itself creates the arc. And if wire itself is creating the arc, that means VF. VF is feedstock, the vector corresponding to feedstock, and source is the both are coaxial in that case, because wire itself is creating arc, and both VF and VS are always parallel. And if as they both are parallel and you are moving on a plane trajectory, for example on a plane substrate, then always these vectors VF and VS both will remain perpendicular to the direction you are moving, because gun is always vertical, and hence this process is inherently omnidirectional. There is no need to have any additional thing in this case. So I can claim that MIG welding process are inherently omnidirectional. That why you move in any direction by using MIG welding, you will get the same property. Just at least because of the machine tool or this omnidirectionality phenomena, no issues will arise. However, the condition is not same when you use tungsten inlet gas welding, or plasma welding, or laser welding, or electron beam welding, or cladding. In that case, VS and VF used to come from two different sources. The source itself is not the feedstock. Like in the MIG welding case, wire was itself creating the arc. In this case, when we use non-consumable electrode type of thing like tungsten inlet gas, plasma, laser, or electron beam, the source is separate, and in the molten pool created by the source, we feed the wire or powder. And hence, it may happen that these three vectors may not remain consistent throughout the process when we deposit on non-linear trajectory, and hence the process is not inherently omnidirectional. So we have to make it omnidirectional. So like I explained, you see in this diagram on the left side, this is the MIG welding. Here, VS and VF both are collinear. Both are coming from the top. VF and VS both are, because my VF is the source of VS. And hence, they will always remain perpendicular to VD wherever you move on the substrate. In that case, it is omnidirectional. But if you see TIG, VS is vertical, created by the tungsten, while VF is fed from the side. Now, if you see, VD is going in Y direction. Assume that VD is in X direction. In that case, the angle between these two may change, and hence the issues will arise. And this will keep on happening. The relative position may keep on changing, and hence angle keep on also changing, which will create the issue for the omnidirectionality. Now we'll go to our next discussion. How can we achieve omnidirectionality? We have identified the issue. We have seen that VS, VF, and VD are not consistent in this case. Their relative positions are changing. Hence, we have to do something. What we can do? Methods of achieving omnidirectionality in directed energy deposition. First is make these two coaxial feedstock and fusion source. which is happening in MIG welding. I mean, if you see carefully, VF is itself creating the source, VS. Sorry.
Sir, I think some disturbance, sir. Please carry on, sir.
Okay.
Sir, 1 minute, sir. Please, dear participants, please mute your audio for the smooth conduction of the program. Don't disturb the session, otherwise you will be expelled from the session meeting. Virang Sukla, sir. Virang Sukla, sir. Please mute your audio, sir. Otherwise, you will be removed from this meeting, sir. Virang Sukla, sir. Please mute your audio, sir. Otherwise, you will be expelled from the meeting, sir.
Okay.
Sir, 1 minute, sir. Just we will remove the participant, sir. 1 minute, sir. Yes, sir. Removed, sir. Sir, sorry, sir.
Okay. I'll continue.
Sir,
No, I
1 minute, sir. I
yeah.
think again he is joining, it seems, sir. 1 minute, sir. Sir, Virang Sukla, sir. Please mute your audio, sir. It is disturbing the session, sir. Sir, if you are continuously joining, please mute your audio, sir. We are requesting, sir. You are disturbing the entire session, conduction the program, sir. I think, sir, removed, sir. Sorry, sir. Please
No,
continue, sir.
it is okay. It is fine. I
Yes,
think it was not disturbance also. So I'll continue.
yes, sir. Okay, please, sir,
So
please.
yeah, thank you. I was saying that how to achieve this omnidirectionality in DET. We know the source direction is always consistent. Usually the laser is coming from the top, it will remain vertical. That is not the issue. Issue is the wire feed direction or the powder feed direction, because its relative position with deposition direction keeps on changing. One solution is make that fix, and it should be in line with the VF. I mean, it should be also perpendicular to the feeding direction or the plane on which you are depositing. That is the first case. That is called as coaxial feedstock and fusion source. Both are coaxial, but it is only possible in the case of MIG welding. As you can see, there is steel gray thing here. This type of phenomena you can get only in MIG welding. Other than that, it will be very difficult to get. Then we can eliminate this. It is good only for MIG welding. Other than that, what we can do coaxial fusion source and surrounded by feedstock. That means our fusion source, that is laser or TIG welding or anything, R is going to be in the center, and instead of feeding wire from or powder from one side, we will feed it in a conical form. In that case, wherever you are moving, the deposition vector is moving in any direction, as you see in the top right diagram. Now everywhere material is same available, hence the process becomes symmetric. That means now the conditions are same. Either it's front feeding, there is no front or back feeding in this case now. But it is very difficult to do this thing with wire. We can do this with powder. Now, in the third case, it could be the coaxial feedstock and surrounded by fusion source. In that case, the wire will be in the center, and your fusion source should be surrounded by the wire in a conical form. And hence, now you are moving in any direction, the condition will remain symmetric. This also we will see how we can do. Then the fourth one is dynamically adjusting the orientation vector. This is the easiest way. So what you do, as you can see in the first diagram of the fourth one, the delivery angle is theta, the wire is faded, and moving direction is VD. And the orange color is showing the direction of fusion, that is will remain same, VF is going to remain same. But as this VD is changing, I mean that motion direction is changing, similar way, wire should also change its direction. I mean, now you need a continuously or dynamically changing the direction of feed stroke. For that, you need to have a rotary feed stroke, just so that it can keep on rotating around the wire feed source in such a way that the angle between VD and VF can remain same. And obviously, the angle between the vertical, which is the fusion source, and the deposition vector is 90° always. So that is not the issue. Also, the angle between the fusion source and VF is also fixed because we are delivering at a particular angle only. So that may not also be the issue. Now we'll one by one see how commercially people have adopted it already. First method, let us discuss about the TIG welding. We are going to implement our method 2, method 3, and method 4 for TIG welding. Method 2, method 3, and method 4 for TIG welding. The first one is coaxial fusion source surrounded by feed stroke. So you can have a system like this as you are seeing on this diagram. So why this today's lecture may be important? For example, you want to develop your own DED system or any 3D printing system or any additive manufacturing system. While designing the machine tool, you should consider all these factors so that you won't be having any issue related to at least omnidirectionality. So what I'm claiming here is center is the arc. So instead of feeding one wire, you can feed multiple wires, at least 3. If 3 wires will be fed into the molten pool, then you can move in any direction. It will be not exactly like a cone, like I said in the case of powder, but at least it will eliminate some issues due to the symmetry. Now you can see the top view. If you move in any direction, it will remain approximately same. However, the best possibility could be you feed a cone of powder. Wire is not possible to form a cone surrounding by the spherical, surrounded by the molten pool. Now in that case, it may be possible. But the issue here is powder cannot be used with TIG welding. Hence, this is the solution for TIG welding. Now, another method 3 is coaxial feed stroke surrounded by fusion source. Now, what we are saying, from the center, we should feed the raw material. That could be wire, obviously, because I already said that powder is not possible in the case of TIG. So, wire is coming from the center. Surrounded should be the fusion source in a conical form. How we can do that? There are systems available. I have seen few patents also. The tungsten is hollow. So TIG welding tungsten is hollow, and you can feed wire from the center. And that hollow tungsten will create a donut-like source, and hence you will have a top view of this can be seen on this diagram, left side and right side. These type of systems can be used. In that case also, you can see you can move in any direction. The angles will remain consistent. Hence, process is omnidirectional. Now the last one, which we have also developed, and from there only, this point words only after like 3 or 4 years before we got the motivation on working on omnidirectionality phenomena, is the dynamically adjusting the feed stroke or deposition direction. So what you do, you have a TIG welding here, as you can see on the left side diagram. It is creating some arc and you are feeding fire from side. Then to maintain the direction consistent, you keep on changing the position of the substrate. So for example, you want to deposit this cylinder. So this cylinder, if you move this whole system, which is TIG plus wire around this, then back feeding, side feeding, front feeding, and then again side feeding will occur. But if you rotate, just keep the whole thing at the same position, but rotate the substrate. In that case, you will be easily feed the wire into the molten pool, and hence the direction between the VS, VF, and VD will remain consistent. This is called as omnidirectionality through dynamically orientation of the workpiece. In that case, workpiece should be attached with a rotary table. Or what you can do, you can make an arrangement which we have also developed. The wire feeder should rotate around the arc, as you can see on the right side diagram. There is a bearing with the TIG welding, and on that bearing, the wire feeder is rotating. So if there is a change in direction of VD as it is on the circular profile, then again the wire feeder will also keep on rotating. So these are the two systems. These are the videos, but I'm not sure because I may not be able to run these videos here. But in the end of the presentation, I'll go back to my computer, see whether my internet is good. I'll show you these videos in the end. But you can see at least in the right side diagram, that system which we have developed. There's a tungsten in the center and wire is feeding from the side, and this wire can rotate freely around it. And this was connected with our controller, and hence we programmed in such a way that based on the tool path position, the wire feeder takes the desired position automatically. This paper is also published in virtual prototyping 2 years back. Now, method of achieving omnidirectionality in DED using laser cladding. Now, laser have a very important flexibility here, that laser can use powder. As I say, laser can use powder. Then you can see on the left side diagram, the method is coaxial fusion source surrounded by feedstock. Center will be the laser surrounded by the feedstock. So feedstock here can be in the form of like a cone. And that is what you have seen in most of the additive manufacturing processes, this type of process. And today, I'm sure you will be able to know why they are doing it. The main reason is so that you can move in any direction without an issue, and hence the process become omnidirectional. So this is the most popular left side one. The right side, sometimes instead of feeding the like a cone, they feed 3 nozzles, like 3 discrete wire. So we call it as discrete channels, like 3 wires also. In this case, you can have different multiple different streams of powder, and you can make the on-spot alloys. It is also similar. The direction will remain consistent because you are feeding from all 3 sides, and hence approximately process will become omnidirectional again. Other method could be, but this flexibility now with laser is much easy, because we can easily split the laser. We can really play with the shape of the laser. The one you are seeing on the left side, one is feeding powder in the center, and laser is in the form of cone. It's a hollow laser, then getting converged. This is very recent. I have recently seen this process. Now people are going towards this because the benefit here is very high material efficiency. You see that powder is coming from the center, and nozzle is the entire powder is surrounded by the laser. That will make sure everything get melted, nothing get wasted. So the efficiency of the DED may increase with these systems, and it should be called as coaxial feedstock surrounded by fusion source, and fusion source is here in the form of cone. Then come to the second one. It is not difficult, I'll say space consuming method to convert a simple beam to a conical hollow beam, like you see here. Like a hollow beam conversion is a bit, lot of optics is required. The system already is developed. It is by okay, so it's a US based company. I'll tell you the name in the end, which have done, those have implemented this method, which is on the left side. But I have seen the system, it is very big in the size and difficult to mount on a robot. While the right side one, in that case, what they do, they split the beam into 3 beams. Splitting is easy. We can use prism and all, and easily we can split the beam and then again converge. Or you can use 3 different laser also. Some Chinese I have seen, they have developed such system where 3 lasers are used directly, and they are merged at a point. Center is the powder or wire. Now it is again omnidirectional. We also have a similar kind of system developed by Fraunhofer, where they have splitted the beam into 3 parts, and center is fed by the wire, and it is an omnidirectional system. I'll show the video in the end. Now last is dynamically adjusting feedstock delivery or deposition direction, like we discussed in the case of TIG. We can do here also. But in this method, as discussed last time also, a consistent vector is maintained between the VF and VD, direction of feed wire or feed material or feed stock, and the direction of deposition or the path of deposition. But this method requires dynamic adjustment of either feed stock or the substrate. This dynamic adjustment is bit tricky. This is because uh, the inertia is involved. And because of the involvement of the inertia, response time is bit less. You give the command, it will take time. For example, you are moving in a path and there is a sharp turn, like you are moving in a V. So when the corner of V will come, process will move, but wire or laser will powder delivery system will take time to take the position, new position, and hence due to this issue, inertia based issue, it takes time. Also, it can be observed that the powder delivery is suspended in a stream of gas rapidly changing in the feed direction. It could lead to decrease in catchment efficiency also. So side feeding is not really preferred nowadays in laser cladding system because of two reasons. One is not omnidirectional. Second, the catchment efficiency is really bad. Now we have already seen TIG welding, laser. Now we will discuss about the electron beam cladding. In the case of electron beam cladding, which is usually performed in vacuum, is very successful processing any metal. Since most of the powder feedstock handling system uses organ, they used to deliver the powder with the organ. The existing electron beam cladding system based GED processes are not with the powder. Although here in IIT Guwahati, we are trying to develop a system which can deliver powder under the vacuum, in the vacuum under the gravity only. But till now, there is no such commercial system available. And hence, electron beam based GED systems are limited to only wire, because wire can fade without any organ. So let us try to apply all these three methods. Third is coaxial fusion source surrounded by feedstock, means from center the electron will come and surrounded wire will come in a very similar fashion. Like I said, in laser we can use powder, here we cannot use powder. So only three wires can come from three sides, very similar to the one we discussed for TIG. However, still there is no such system available. Coaxial feedstock surrounded by fusion source. Like we split the laser, we can split the electron beam as well, because that can also be done easily with the help of magnetic coils. In laser, we play with the laser by the optical lenses. Here we play with the electron beam by the electromagnetic lenses, so-called. So what we can do, we can have the single beam of electron beam that can be split into three parts, and then again it can be merged at a particular point to create the molten pool. In that molten pool, you can feed the wire, powder. Powder is not possible, like I said, because all are pneumatic. But if under gravity, why not? You can feed. Also, you can create the conical shape of electron beam as you see on the right side. This type of system is already available. And yeah, there's a Chinese company. I have to recall the name. They have developed a system where the cathode, which is generating the electron beam, is in the nature of hollow. So it's like a hollow cathode. Cathode itself is a hollow. Because it's hollow cathode, at an angle, it will generate a hollow beam, hollow electron beam. And that hollow electron beam is when it gets converged after a particular point, it will converge to a solid beam. In the meanwhile, you can feed the wire from the center, as you can see in this system. So this type of systems are also available. You know now the reason. Reason is to achieve the omnidirectionality, nothing else. Or dynamically adjust the wire feed direction. Like I said, this type of system has also been implemented by SIACI. SIACI is the leader for electron beam based system for wire deposition. They have implemented this method in their commercial systems. It's a very expensive machine. If you see this video, I'll show you that. And also the wire is fed and continuously it can rotate also around the molten pool. And why it rotates? We know that they want to maintain either front feeding, back feeding, or side feeding, a particular type of feeding all the time when the deposition is happening along the trajectory. Now we'll move to another process, which is omnidirectionality in material extrusion. Material extrusion is nothing but like your FDM process. So the extrusion-based AM processes are typically identified by nozzle, which is also called as extruder, through which the material under pressure is forced out and deposited on the print bed. Fused deposition modeling is the most common extrusion-based AM technology for polymers and plastics. FDM is generally assumed to be omnidirectional in nature as the material is extruded through a circular orifice, resulting in uniform tracking dimensions. But if the material extrusion is in the field of constructions, they have a unique challenge. And that is, unlike the FDM, in FDM process, if you see the orifice is circular, they used to have a square nozzle or rectangular nozzle or oval nozzle. This assures the ease of stacking of layers. That is why they do this. Because in the FDM process, you basically have heat involved. Heat is involved that makes the pre-built layer flat. That is the phenomena is also called as bead ironing. Bead ironing is not really possible when you deal with the cold material, like in the construction industry. Nowadays, it is very much popular, the concrete printing. In that case, you cannot really make it flat if you are not using either oval kind of shape of bead or, for example, a rectangular nozzle. Now, the issues are there. If you are, for example, using a rectangular nozzle, just carefully look into this diagram. The figure below shows a print bed for rectangular zone A, B, and C. You see that center is the nozzle size, and this nozzle is having a width of B and thickness A. The XY dimension of the rectangular nozzle is A and B. Now, if you move left to right, you will get B width of the deposited bead. If you move up and down, you will get A width of the deposited bead, and if you move diagonally, you will get C width of the bead, and in between, you will get A to B. So this highlights the non-omnidirectionality nature of this nozzle. What is actually happening? You are depositing different bead size at different location. Hence, the process is not omnidirectional. So track deposition without any consideration to geometric uniformity often lead to twist in the track. So for example, you are making a 90-degree turn, then definitely a twist in the deposition will occur. If you just think of it, you are depositing with a rectangular bead and take a 90-degree turn. What will happen? A twist will happen on the corners. What we need to implement the method. So mostly in this type of systems, method 4, which is dynamically adjusting the feedstock delivery for deposition direction, is implemented. Similar to TIG and plasma, in this method, the deposition head is held vertically and stationary while substrate orient itself, such as the geometry based on the path, or sometimes the head also rotates. As you can see in this diagram, when I'm moving on a nonlinear trajectory, what is happening? The head is also rotating. It is not coming in the straight line. If head was coming in a straight line, different widths you will achieve in between. Hence, to make the process omnidirectional, you need to rotate it. And this is all happening because these three vectors, one of these vectors is creating the issue. In this video, I'll show in the end that how this head is rotating while depositing. And now you will have the answer why they are rotating the head. They are doing nothing but trying to achieve the omnidirectionality. Now we'll move to wet photopolymerization. So today my objective is to show you that each and every AM process uses some auxiliary system to get this omnidirectionality. But today what we are trying to do is trying to give a name to it. So most stereolithography processes use a galvanometer. Galvanometer is nothing but a device in which mirrors are attached on the motors. When the laser beam strikes on the mirror, and as the motor which attached with the mirror change the angle of incidence, the beam can project here and there and scan the bottom powder bed or the liquid bed in this case. So laser beam strike the built surface at an inclination to the vertical, results in elliptical spot rather than circular one. So if you see on the right side diagram, if the beam is coming in the center, it will be nothing but a circle. But if you are deflecting it away, then it will become ellipse. You can easily identify it. If you cut a cylindrical object at an angle, you will get nothing but the ellipse. So that is what happening here. So the diameter of curing is center, it is circle, but away from the center, it is becoming ellipse. Why it is happening? Let me try to just reconnect with our definition. Here, VF is 0 because liquid is always lying on the bed. There is no vector associated with the feed stroke. VF is 0. Now there are two vectors, VD, that is deposition direction, and VS, that is the source vector associated with the source. In this case, the laser which should come perpendicular to the bed, getting inclined, and hence the angle between the deposition direction and the source of fusion, which is laser, is changing. In the center, it is 90 degree. In the corner, it is some angle, and it's keep on changing. An inclination of 45 reduces the density by 30% and increase the interaction time by 40% at original travel speed, and hence spoils everything. This beam distortion inherently changes processing parameters during the part fabrication, thus processing non-homogeneous build part. So what you get here due to this non-homogeneous part. Given the fact galvanometers are used to scan the geometry in the SLA system, but some beam correction has to be done to assure the omnidirectionality. Now this correction we are not going to do in the system side, in the process parameter side. If you do that correction process parameter side, that will not be the omnidirectional. You are going to do something with the machine tool system. So what they do, from the above discussion, it can be inferred that the wet photopolymerization is a pre-placed, like I have already explained, where energy beam VS does not remain perpendicular to the travel direction VD throughout the build. It changes. Some angle is coming. In the center, it is 90. Away from it, it's something else. Thus, the process is not inherently omnidirectional. Therefore, we have to implement something. In succession to our previous discussion, we have discussed 4 methods. Here, a new method is going to come, and that is called as fusion source beam correction to ensure omnidirectionality in this case. How we achieve this? We actually correct the beam. How we do that? So there is something called as F theta lenses. So a galvanometric system is restricted to motion the workpiece in XY plane and the laser head, unlike flying optics. Flying optics, I'll explain to you. Why we use this galvanometer? Because we can move our beam, we can deflect the beam with a very high speed up to 1000 mm per minute. And it can be obtained only because of the low weight involved with the mirror in the galvanometer. Just those mirrors just keep on reflecting, and you can move the laser beam on the bed with a very high speed. But like you see on the left side diagram, the focal point will remain circular only at position, only on the trajectory which is shown in blue color. That is the circular path. You can appreciate this because in this path only the cross section will be circular. But if it will fall away from this, the focal length will change, and hence your diameter is going to be something else. Therefore, you need a correction. You need to change the focal length. How we can do that? So there are some lenses. Immediately after, as you see on the right side, immediately after getting deflected from the galvanometer, the laser beam used to strike on F theta lens. F theta means it corrects the focal length based on the angle of incidence. That is theta. So even if the theta is changing, focal length remains same, and it falls like this. You see here vertically almost. In that case, you see what they have corrected. They have done nothing. Just maintain the direction of vector of fusion source VS. So VS is now perpendicular to VD all the time, and hence we can say that this process is now omnidirectional, but only when you implement this F theta lens here. So this is the 5th method, which we call fusion source beam correction, GSS based method. Other than that, what you can do, very simple solution. Unlike galvanometer, where we use mirror to deflect the beam, use flying optics. Flying optics means you just mount your laser head on a XY table, or you keep your powder liquid bed on the XY table and move it under the laser. In that case, you are not tilting, please note, you are not tilting the laser. As you can see on the left side diagram also, laser is coming vertical in that case. But what you are doing, you are just capturing it just perpendicular to the plane all the time, and hence the angle will remain maintained, and it will be omnidirectional. The issue here is speed will be less, because now you are going to move the system. We know that liquid based systems are the most accurate additive manufacturing system, produces layer thickness up to 5 microns or even less. In that case, they are the best additive manufacturing process. Those can give you the surface accuracy. If you are going to move something, some waviness will be there in the wet tank, and hence you may have some issues. So you have to move very, very slowly if you really want to move any of these two things. So system will become slow, scanning speed will go, but process will remain omnidirectional. Therefore, I would like to mention today, as this particular the focus of this workshop is on micro devices. If you want to develop a system for photopolymerization based, but want to focus really on the accuracy, instead of going for the galvanometer, if you go for flying optics based system for a large tank, process will be slow, but you will be able to get really micro level parts. Another way of fusion beam correction is irradiating a laser a layer at a time. This is what you have seen in most of the nowadays system. SLA, where the galvanometer used to move the laser beam around the wet photopolymer, now has been usually replaced by a method called digital light projection, or DLP. They uses digital mirror devices. It is just like your conventional projector. In that case, the layer which we want to scan, only the corresponding mirrors get deflected, and the projection of that portion of light only projected on the bottom side, and hence everything is always perpendicular. The direction, everything remains consistent, because the entire layer is associated with one mirror. Each and every location of the system is now associated with one mirror, and hence, based on its opaqueness and the transparency of the corresponding mirror, the layer gets scanned, and hence no issues for the omnidirectional. So this is the sub method of method 5, that is the fusion source correction, irradiating at a layer. Can I take 1 minute break?
Yes, sir. Yes, sir. Yes, sir.
Sorry.
Yes, sir.
Sir, I'm in a lecture. I'll be done in 20 minutes. 3:30. Oh, okay, sir. So after 3:30. Okay, so I'm sorry. Omnidirectionality in sheet lamination. So in the case of sheet lamination based processes like FSW, this I think if I remember correctly, I have given a brief highlight that how FSW can be used. Sheet lamination is a AM process that employs pre-placed feedstock. In this, feedstock doesn't move. Shaping the feedstock corresponding to the layer geometry can be carried out by multiple means. For example, in the case of paper, if I want to join two papers together, the layer is carved either by mechanical knife or laser, and then they are joined together. Also, the source of fusion for various sheet based is different. In the case of metal, it may be ultrasonic vibration, it can be FSW like I have mentioned, or it can be chemical or adhesion based. Now let us check for the omnidirectionality of sheet-based process. So sheet-based AM process fall under the category of inherent omnidirectional. They are all the time, because your fusion source is always vertical, sheet is always at 0, and direction is always changing. As the source is always vertical, they are always inherently omnidirectional. But there is laminated object manufacturing of paper where knife is used to cut the layer. In that case, some issue comes into the picture. If you are cutting by laser, then definitely you can use f theta lenses and make the process omnidirectional, not an issue. But if you are using knife, knife is not an omnidirectional tool. So I mean, you are cutting a layer by using the knife and then stretching it. That is how it happened in the LOM process, laminated object manufacturing by Kira, K-I-R-A, Kira's loom. In that process, they cut the layer and then they join this layer with the previous surface. A knife, if it is used, in that case, what may happen? The knife has to cut the sheet. And as you can easily appreciate, if you are changing the direction, then the direction of knife should also change. It is quite obvious, and hence the process will be only omnidirectional if you will provide some rotary axis with the knife, and hence the process will require additional controller. Or you can use energy beam. Then definitely you can eliminate this issue by applying the f theta lenses. Now we'll come to, as you are seeing, as my discussion is going on, you can observe that I am not discussing now. The processes are more inherently omnidirectional. We discussed a lot when we were discussing about the DED. Then after that we discussed about the powder bed fusion. UV light based system like wet photopolymerization. But now slowly you will see the processes are inherently omnidirectional. In this, auxiliary arrangements are really not required. So like for example, powder bed fusion, it is very similar to wet photopolymerization. Instead of the liquid bed, here the laser will be on the top, that will be scanned by a high power laser will be there on the top, that will be again scanned by galvanometers. Here also you can apply the method 5A and B, where you can use either the theta lenses or you can move the beam using flying optics. So here again the representation is there. So any system, if you are going to buy for powder bed fusion, you can always ask whether there is what is the mechanism for beam correction. They will say that there is optics for beam correction, or they will say there is a f theta lens mounted that will correct the beam shape. Or another method is use the flying optics in a very similar fashion. That flying optics means you move your laser beam on the bed in such a way that the laser will always remain perpendicular. The second last actually is the omnidirectionality in material jetting. But fortunately, they are inherently omnidirectional in nature. So because in this case, the material is coming perpendicular to the substrate, and actually the source of energy here is nothing but the solidification time. So that is also coming perpendicularly. I mean the binder is already mixed with the material, then definitely there is no need to have any additional source vector here. That means the Vs and Vf will remain parallel to each other because they are mixed in the beginning itself, and then you are always depositing perpendicular to the substrate. But if you are injecting it at an angle, that is the issue. But usually we do not do that. In any additive manufacturing process, when you are looking for it, you can observe, like for example, object is the process where material jetting used to happen. You will see material is always falling perpendicular to the substrate. Then there is no issue. But if there is an inclination, then the issues may come. So as you can see here, the particle. This is another process for material jetting apart from the non-metals. Apart from the non-metal, this is the metal-based process in which cold spray. In this, material is jetted on the substrate and it is always perpendicular. There is no issue. Omnidirectionality in binder jetting. Binder jetting means, in this case, the substrate, on the substrate you have powder, and from top the binder will come. Similar to material jetting, binder jetting based processes are also inherently omnidirectional because binder is selectively deposited on the powder bed, which adhesively joins the particle together with the build geometry layer by layer. And this process keeps the fusion source, which is chemical addition, perpendicular to the travel direction throughout the build. And since the feedstock is having zero velocity, that is Vf is zero on the print bed, the process falls under the category of inherently omnidirectional. Now I'll conclude this presentation with some remarks, and then I'll just try to connect the PC again to show you at least 2-3 videos quickly. So the selection of an appropriate method to achieve omnidirectionality for any given problem required careful consideration for various factors. More often than not, the selection criteria mostly involve establishing a balanced trade-off between various desired outputs. But that should not be the case. For example, in method 5, we use flying optics for beam correction in wet photopolymer, and powder bed fusion provides a robust solution to achieve omnidirectionality, at least for micro components. Those could be the best method, but really, till now, nobody has explored these methods much. On the other hand, the use of galvanometric systems with the f-theta lenses provide high print speed, definitely, but they are limited to smaller print area. And that is why we all have a limited print area in the powder bed technology. Usually they are limited to 300 by 300 by 300 meter. Height doesn't matter, but the XY is something really important. They really can't go with a single laser beyond 300 by 300 by 300, and that too is the largest, I think, by DMG Mori. Otherwise, they are limited to 250 by 250 by height can be like anything, but usually 250. Just a summary, I'm going to tell the limitations and the advantages. The method 1, which is coaxial feedstock and the fusion source, best method, but only limited to MIG welding. Method 2, where coaxial fusion source surrounded by feedstock, means center laser, center electron beam surrounded by feedstock, can be different types, like discrete, multiple nozzles you can feed, but relatively low catchment efficiency. You can use conical form of powder, but in that case, you cannot tilt the head. If you tilt the head, the density on the cone will be different. You can feed 3 different wires, but not very compact. It will be a very huge system. 3 wires coming on 3 sides, and also print delivery pool should be large in that case. Hence, the process may not be very accurate. Non-pneumatic powder delivery system definitely can do help in electron beam system, but still there is limited work has been done, not significant. We also trying here in IIT Guwahati to develop this type of system. We'll see. Then method 3rd is coaxial feedstock by fusion source, in which center will be the feedstock and from surrounding the fusion source will come. We have seen in laser cladding, it can be achieved, but manipulating the shape of laser is a bit difficult task. Only experts can do that. Laser cladding and electron beam cladding with 3 beams, yes, that is easy. You can easily mount 3 guns. Like I said, then the few Chinese systems are also there. They need not to have the expertise in the laser. Just buy 3 system, 3 laser, mount 3 lasers at an angle of 120 degree and do the job. You can use the hollow cathode, but difficult to fabricate such cathodes. Multiple equally spaced high frequency oscillating electron beam, but again the setup will be expensive and expertise in the electron beam is required. That too is limited in the literature, and this type of system is going to develop in IIT Bombay. Dynamically adjusting the feedstock, easiest way to do that. Dynamically, you either change the orientation of the deposition vector by changing the direction of feedstock or substrate. It is slow in response. Additional setups are required. Difficult to integrate with the system, and it requires some additional setups always. Response time is the major issue in this case. Like if I'm going with a very high speed, it takes some time to take the new position when we deposit on a nonlinear trajectory. Fusion source beam correction, obviously it's a method in which we can correct the shape, but it's still complex fabrication. You need to have the knowledge of the lenses. Like in the case of in the case of laser, it is f-theta lenses. Definitely you can use flying optics, like I said, but slower is the process. Otherwise, it is very robust. Irradiation at a time, you need a small, usually have small printing area, like in the projection system, and you need to have the DMD system. You have to buy the digital mirror devices in that case. Or you can use high energy, use of energy beam. In that case, again, you can use the flying optics, or you can replace the cutting tool, like in the case of knife, with the laser beam. So knife can be easily replaced by the laser beam, but again, printing area will reduce. or you can replace the knife by flying optics. Flying means the laser beam can move, but again it will become slow. So this use of energy beam method 6, which I'm talking about, is only for paper. So final remarks for this are the omnidirectionality implies invariance in the material and geometric property of as-built part process various AM platforms. The process of binder and material jetting are inherently omnidirectional. So whenever you are buying any of this kind of system, you need not to worry much. But use of F theta lenses, layer irradiation, flying optics are suitable method for achieving omnidirectionality in wet photopolymerization and powder bed fusion, which is similar to wet photopolymerization in the context of omnidirectionality, employs F theta lenses and flying optics. FDM is omnidirectional, not an issue, we know that, because circular is the nature of the orifice. But if the extrusion nozzle is not circular, it will not be omnidirectional, and hence you have to do additional things like we have seen in concrete printing. Majority of DED systems are not omnidirectional at all, and you have to rely on achieving the omnidirectionality with the several methods. At least all 5 methods were associated with DED. With this, thank you very much. Now I'll try to connect through my PC at least once, and I'll try to show you the videos if possible. Otherwise, we can stop here. Thank you very much.
Sir, we will wait. We will wait, sir. You please connect with your system, sir. We will see that video, sir.
Yeah, I'll try. I'll try.
Yes, sir. Thank you, sir. Thank you, sir.
So I have connected here. I hope you are able to. Okay, this is my presentation only. Now I'm going to stop. How to stop here? Yeah. Now I'll try to share from here. I hope you are able to see.
Yes, sir. Coming, sir. Coming, sir. Yes, sir.
So you can see that.
Yes,
This
sir.
is
That
the in this
video.
DED, you can see that the deposition is happening in a conical form. Center is the laser, while this bottom one is the conventional one. If it get disconnected, please let me know.
Sir, video is stopped, sir.
Stop now.
Yes, sir. Yes, sir.
Yeah, it's again connecting.
Yes, sir.
Okay, what I'll do, I'll just try to show it. Uh, okay, let us do this today.
Okay, sir. Otherwise.
No. Let me. What I'll do, I'll share the screen. I'll just
Okay,
disconnect
sir.
here, and instead, I will switch on my camera, but I'll show.
Okay, sir.
You can see.
Yes, sir. Yes, sir.
So I was talking about the DED system. You have already seen the DED. Now I'll show
Yes, sir.
you how it is happening in the case of TIG welding. TIG welding, if you see this video carefully, it is moving in a circular direction. Right now it is front feeding. Now it is becoming side feeding. Now it is becoming back feeding. This is what used to happen. Then again it become side feeding. We don't want that. So for that, the solutions, I have already explained everything. Only the solutions I'll show you. 2 solutions I have suggested. One is rotate the substrate. So what we can do, if you see carefully the same case, I'm trying to deposit and rotating the substrate. It is front feeding, right? And hence the consistent deposition. Then again, in another case, if you see the rotating wire feeder. Here I'm rotating the wire feeder. Fine. Other systems is splitted laser beam. In this case, if you see, this is a system developed by Fraunhofer. Center is coming the wire, and 3 beams are coming from 3 sides, creating a uniform molten pool around the wire, and hence the process can become omnidirectional. It can move in any direction. Now I'll show you how it happened in Siaki, electron beam. They also rotate. If you see that, they have additional C axis which is continuously rotating. So yeah, here. Okay. So they have this C axis. Yes. Yeah. So this C axis, it keeps on rotating while they make the circular or any kind of geometry. They used to rotate the substrate in this case. Other than that, I'll just show you the video which is of concrete printing. Here also you can see carefully the bottom part is rotating, right? It is rotating only because it want to accommodate the errors on the corners. Otherwise, the corners will bend. So these are the videos only. I hope it is clear now.
Yes, sir. Yes, sir. Thank you, sir.
I'm sorry for the network. It's bad. Now I have another lecture and I don't know how it will happen.
Okay, sir. Okay. Sir, shall we go with the question and answer session, sir?
Yes, please.
Okay, thank you, sir. I request the participants, please unmute yourself and you can ask question directly to our resource person, or you can type your question in the chat box. We will ask on behalf of you. Sir, one question in chat box, sir. Should I ask, sir?
Yeah.
This is the question from Professor Kumar Yadav. Sir, what will be the rate of cooling or solidification of metal through this process and the speed of welding?
Okay, which process you are talking about?
It is not mentioned, sir. Through this process means it is additive process.
TIG, fine. So TIG usually give you 15 gram per minute, and then you can consider the cooling rate. It keeps on changing. If you have a large substrate, the cooling rate will be something else. If you keep on building and you are reaching at a top level, very thin layer of very thin wall will be there to transfer the heat. So I cannot really comment on the cooling rate. It depends on where you are printing. If you are printing on the substrate, cooling rate will be high. If you are printing on top of some layer, I mean at a height, then the conduction will be less. Only convection will be the major phenomena. So it keeps on changing.
Thank you, sir. I request dear participants, please unmute yourself and you can ask question.
Yeah, directly. Yes, please.
Yes, directly to our resource person, or you can type in chat box. We are getting a lot of positive responses, sir, in the chat box. Yes, thank you, sir. Thank you, sir.
I'm sorry about this internet issue. I thank this internet.
Yes, sir.
Today.
Sorry. Okay, sir. Okay, sir. Yes. Sir, shall I continue with vote of thanks, sir?
Yeah, or thank you very much.
Sir, thank you, sir. Just 2 minutes, sir. I will wind up, sir. Just 2 minutes, sir. Thank you very much for this wonderful presentation, sir. Your presentation added more value for this 1 week STTP program. Really, it is excellent presentation, sir. We have gained more basic knowledge about additive manufacturing system from your presentations. You have started with additive manufacturing, CAD file, STL file, sliced file, and 7 process classified by ASTM. That too from low energy consumption to high energy consumption. Then omnidirectionality, equally sensitivity of the process in all the direction you have explained. And you explained omnidirectionality with isotropy. What is the difference? And the importance of omnidirectionality and the special orientation of 3 vectors and the method of achieving omnidirectionality in DED and TIG and plasma welding. Omnidirectionality, dynamic orientation of workpiece and feedstock delivery. And you have explained many methods like deposition using laser cladding and deposition using electron beam cladding and omnidirectionality in metal extrusion, material extrusion and omnidirectionality in wet photopolymerization, fusion source beam correction mirror to deflect flying optics and irradiating layer at a time. These are the explanation given. And omnidirectionality in sheet lamination and dynamically adjusting the cutting edge, omnidirectionality in power bed fusion, omnidirectionality in material jetting, omnidirectionality in binder jetting, and you have concluded with the advantages and limitations for all six methods. Thank you very much, sir. It is really a very informative session, sir. Now I request our convener to conclude this session with the thanks to our resource person. Requesting Professor Chandrasekhar, sir.
So, good afternoon, sir. Is it audible?
Yes, yes,
Yes,
yes.
Sir. Good afternoon, sir. Sir, on behalf of management, principal, Department of Mechanical Engineering of SVCE and the participants of STTP, thank you very much for accepting our invitation.
Sir, voice is breaking, sir.
No, I can hear.
Sir, sorry, sir. On behalf of management, principal, Department of Mechanical Engineering of SVCE and participants of STTP, thank you very much for accepting our invitation and delivering an informative and thought-provoking webinar on omnidirectionality in additive manufacturing systems, organized by SV College of Engineering, Tirupati, in spite of your busy schedule. Thank you very much, sir. Thank you, Sergeant, sir.
Thank you very much, sir. Thank you. Thank you very much.
Thank you. Thank you.
Thank you, sir.
Thank
Dear participants, our today's session ends here, and our tomorrow session or morning session, Professor T. Murugesh from Amtech Instruments. Topic is ultra precision technology, and afternoon session, Professor Carmel Mary Esther from University of Munster, Germany. Topic is functional behavior of oxide thin films and characterization challenges for smart and futuristic applications. I request dear participants, please join 9:50 a.m. so that we will start the session exactly at 10 a.m. Thank you all.